Hey everyone, and welcome to this explainer. Today we're doing something a little bit different. We are going to dive right into an active, real-time investigation into something truly extraordinary: how your brain builds the reality you see every single day. We all walk around assuming we're just passively recording the world like a video camera, but let's actually investigate the hidden blueprints our brains are using to construct our reality.
Right now, I want you to just take a quick second and look around the room you're in. Pretty effortless, right? You see shapes, you see colors, objects, depth. But in this exact millisecond, your brain is actively filtering out massive amounts of data and heavily constructing everything you are experiencing. You aren't just passively seeing the world, your brain is actively deciding what you should see.
Okay, so here is our roadmap for today. We're going to cover 1. The gateway of attention. 2. Sensation versus perception. 3. The rules of grouping. 4. Perceiving depth and color. And finally, 5. When our brains are tricked.
All right, let's jump straight into Section 1, the gateway of attention.
Before your brain can even begin to build a coherent reality, it has to decide what raw materials to actually let in the door. Attention is literally the ultimate filter. So what exactly captures it? Well, it's basically a tug-of-war between two main determinants. On one hand, we have physical external factors. If something is intensely bright, large, colorful, or suddenly moving, it grabs you, right? But on the other hand, we have psychological internal determinants. Your own internal state matters just as much. I mean, if you're biologically hungry, you are absolutely going to notice a food sign you'd otherwise completely ignore. Your emotions, your personal needs, and your interests dictate your focus just as powerfully as a flashing light.
Moving right along to Section 2, Sensation versus Perception.
Have you ever really thought about the massive gap between the physical act of light hitting your eyes and the complex psychological experience of recognizing a close friend's face in a crowded room? We can actually map this gap out in a highly specific one-line flow. It starts with a physical stimulus, like light or sound, which is picked up by your sensory receptors. Then, through a process called transduction, your organs convert that stimulus into electrical nerve impulses. Those messages travel straight to your brain, where specific areas process the basic features. And then, the real magic happens. The brain organizes the sensory input into meaningful patterns, which leads us to the final step, interpretation. That is where you actually consciously recognize what you are sensing.
So the absolute crucial takeaway here is clarifying this fundamental difference. Sensation is essentially just a biological data collection process. It's your eyes, ears, and skin simply picking up raw visual or auditory stimuli and transmitting them. Perception, on the other hand, is entirely psychological. It's the sophisticated method by which those raw sensations are actively interpreted and organized into a meaningful experience.
Which brings us to Section 3, the rules of grouping.
Perception doesn't just happen at random. Our brains utilize a set of hidden, hardwired rules called the Gestalt principles. Gestalt basically just means that we have this natural tendency to force patterns onto whatever we see. We forcefully organize isolated, raw stimuli into coherent, unified groups. It's exactly why you can easily focus on a single friend's voice in a completely crowded, noisy coffee shop. The first of these rules is the figure ground principle. This is your brain's absolute refusal to tolerate visual ambiguity. When you look at a scene, your brain instinctively forces you to decide what the primary object of focus is, that's the figure, and what is merely the backdrop, or the ground. You literally cannot perceive a scene without your brain making this split-second classification.
Now, this is where it gets fun. Take a look at this classic reversible figure, and notice how it kind of turns your brain's figure ground rule against itself. You might initially see a white vase on a black background, but keep looking, and suddenly it flips. Now you see two black faces in profile looking at each other against a white background. Because the visual cues here are perfectly balanced, you can actually watch your own brain software switch back and forth in real time as it struggles to decide what's the figure and what's the ground.
Okay, another major rule is the principle of similarity. Simply put, this is our tendency to perceive things that look alike as belonging to the same group. Think about being at a massive sporting event. You can effortlessly track the members of your favorite team as they scatter all the way across a chaotic field. Why? Simply because they're wearing the same uniform color. Your brain links them automatically.
You can actually feel this happening right now with these dots. Your brain instantly, and without any conscious effort on your part whatsoever, groups all the orange dots together into one visual category and all the purple dots into another. The similarity in color completely overrides the fact that they're really just a mixed arrangement of circles. Next up is the principle of proximity. This is yet another massive mental shortcut. It dictates that objects located physically close to one another in space will be perceived as part of the exact same grouping. Distance alone becomes the defining factor for how we organize our visual world.
Check out how the exact spacing here completely forces your brain to see three distinct vertical columns of dots. You definitely don't see this as a single unified block of dots, nor do you see it as horizontal rows. Because the vertical dots are situated closer together than the horizontal ones, your brain forcefully groups them vertically.
Now, let's look at Section 4, Perceiving Depth and Color. Up until now, we've basically been talking about 2D organization, but the image projected onto your retina at the very back of your eye, it's completely flat, like a photograph. Yet you experience a rich, stable 3D world. How exactly does the brain pull that off? Well, part of the answer lies in perceptual constancies. Your brain actively maintains consistency in the objects you see, so your reality doesn't constantly warp and distort. For example, because of size constancy, you know a car driving away isn't actually physically shrinking, even though its image on your retina is getting smaller. With color constancy, your brain knows that a red apple is still red, whether it's sitting out in bright afternoon sunlight or under a dim, warm-toned lamp. Your brain just constantly adjusts the math so the world remains stable.
And speaking of color, our perception of it is actually highly psychological. Physically, light just consists of varying wavelengths, but color perception happens when your mind processes this visual stimulus, compares it with memories, and interprets those wavelengths as specific attributes. The physical length of the wave gives us hue, basically whether we see red or blue. The amplitude or the height of the wave translates to brightness, and the purity of those wavelengths combined gives us saturation. It's just a perfect blend of physics and psychology.
And finally, the really fun part, Section 5, when our brains are tricked.
We've spent all this time learning about the incredibly efficient rules and constancies our brain software uses to build reality. But what happens when we intentionally create images that exploit those exact same rules? We get optical illusions. These are moments where your perception fundamentally contradicts reality. Let's start with a classic. Which horizontal line is longer, A or B? Your eyes are probably screaming at you that line A is noticeably longer than line B, but in reality, they are completely 100% identical in length. This is the Muller-Lyer illusion. One explanation for this is that because we live in a world filled with rectangular buildings, our brain is super used to interpreting angles as depth cues. We naturally tend to pull inward-facing angles towards us and stretch away outward-facing angles, which completely tricks us into misjudging their actual size.
And this brilliantly illustrates our next mind-bender, the Ponzo illusion. Once again, both horizontal lines are exactly the same length, but line A looks so much longer. Why? Because of the perspective hypothesis. The two converging vertical lines mimic linear perspective, kind of like train tracks vanishing off into the distance. Your brain just assumes the top line is physically further away, and your internal software reasons that if an object is further away, but it still projects the exact same size on your retina as a closer object, it must physically be much larger. So it artificially magnifies line A right in your mind.
Okay, try this one. I completely challenge you to look at these long, thick diagonal lines and see them as perfectly parallel. It's incredibly difficult. This is the Zollner illusion. The long black lines are perfectly straight and they are parallel to each other. However, that pattern of short intersecting lines creates a completely false impression that the main lines are tilted and skewed all over the place.
The specific reason the Zollner illusion works so well brings us to an amazing concept known as angular displacement theory. As a general rule, when interpreting crossing lines, the human brain has a built-in flaw. It tends to exaggerate acute angles, making sharp angles seem wider, and it completely underestimates obtuse angles. This constant, tiny miscalculation in the brain is the main culprit that makes perfectly parallel lines look completely chaotic, which sets us up perfectly for our final optical trick.
Take a look at this setup, known as the Poggendorff illusion. We have a black diagonal line, let's call it line A, disappearing behind a solid gray rectangle. On the other side, we have a red line and a blue line. Just using your eyes, which line logically connects perfectly with line A? Almost everyone guesses the blue line, line B. But if you were to remove that gray rectangle, you'd see that line A actually connects perfectly with the red line, line C. The intervening gray block forces your brain to misalign the angles completely, proving just how easily our spatial perception can be hijacked.
So we've seen how our mind filters data, groups it, assigns depth and color based on memories, and even crashes when presented with certain lines on a page.
The reality you experience is a spectacular, real-time construction happening entirely within your head. So it leaves us with one final, deeply provocative question. If your brain's internal software can be so predictably and easily tricked, can you really always trust what you see with your own two eyes? Thanks so much for joining me on this explainer, and I hope you never look at the world quite the same way again.